And now we leave the stage to Rémy Degenne, again, from INRIA and University of Lille, who will tell us something about his project, the Brownian motion project.
Thank you, Lorenzo. Yeah, this will be a presentation about formalization of Brownian motion, and at the end I will talk a bit about the continuation of that project, which is work toward defining and working with stochastic integrals. Yeah, okay. So the Brownian motion part of that is joint work with several people because it was an open project. So mainly David Ledvinka, who is now a postdoc at Imperial College London, Etienne Marion, a master student at ENS Lyon, and Peter Pfafferhuber, professor at the University of Freiburg, and several other contributors who also made pull requests to the repository and advanced the formalization. So what are we talking about? We wanted to formalize Brownian motion, which is a stochastic process. So the stochastic process can be seen as a collection of random variables. So for each time you have a random variable that can take real values here and has some specific distribution. Another way to see it, which is more the one that you see on that picture, is that it's also a random variable with values in those paths. That's the functions from time to the reals. And we can kind of think that those paths will continuous on that picture, and that will be important for Brownian motion, but they're not differentiable. And okay, a particularity of Brownian motion is that the way it evolves after some time does depend on the value it has at that time, but not on the path before. So mathematically, Brownian motion is so a stochastic process with a specific distribution. And we will build one which is real valued. So that's a stochastic process from the positive real line to the reals. And it has almost surely continuous path. We will build a particular one that is continuous surely, but we say in general that something is a Brownian if it has almost surely continuous path. That means that those functions from time to bt of omega for any omega or almost all omega are continuous. So we want to build this. The project started not with that goal, but it actually started 2 years ago in 2023, not as a collaborative project at all. It's just with Peter Pfafferhuber, we discussed and wanted to formalize something in probability, decided to formalize the Kolmogorov extension theorem, which is a result that tells you that in order to define a measure on the whole path space, it's enough to build a family of measures on simpler spaces, which are the finite products indexed by finite subsets of your time. So we did this together on our own without having a blueprint or anything, any collaboration tool like that. So to be a bit more precise, it says that if we have a projective family of measures, which is, okay, it's a family of measures indexed by the subsets of times. So for each subset, it's a measure on the finitely many products, a finite product of the value space indexed by the subset that satisfies some projectivity property, meaning that if you have a measure on a subset and you then restrict to a subset of that subset, then the measure on that smaller subset is obtained by mapping the larger one by the restriction. And the extension theorem says that if you have such a family, then it defines a unique measure on the whole path space. Okay, so we did that, and we were looking for like further like formalizations goals, and we decided for Brownian motion. And but sometimes you have other priorities, and you don't do it. So the project stayed dormant for 2 years, and then we decided to actually finish it. We made the observation that we would never do it just the two of us, and so we decided to open it as a collaborative project. So let's have an overview of the construction that we want to do, the various goals of that project. So we have that Kolmogorov extension at the beginning, and so we're thinking with that theorem, we can build a stochastic process that has the right distribution to be a Brownian motion, but that won't give us continuity. So if we can build a projective family of measures for Brownian motion, we want those to be Gaussian, particular multivariate Gaussian measures. If we can build that family, then we get a measure on the whole path space, and from that, it's very easy to get it as a process. So if we build multivariate Gaussians, we can do that. At the time, like in June of this year, MATLAB had one Gaussian. It was the Gaussian on the real line, but nothing more general. So we needed at least Gaussians in RD. We decided to do a detour through much more generality before going there. Then we needed to prove that enough properties of those Gaussian distributions to prove that the family we build is projective, apply the extension theorem to get a measure on R plus to R. And then we want a continuous version of that, continuous modification of that. So we have to prove, well, we proved the Kolmogorov continuity theorem or Kolmogorov-Chentsov theorem, which is something that gives you a modification of your process. So in particular, something with the same distribution, but with a continuous path. So I said it became an open collaborative project. So what does that mean? It means that when we decided to do that, first we had to prepare the project. Like if you just write one message on Zulip telling people, okay, I want to formalize this, and with not much more detail, then maybe you will get a few volunteers, but not many. So there was roughly 3 phases. The first preparation phase, which started it started 2 years ago when we decided, okay, we want to formalize the Brownian. So we decided on the overall proof strategy. And at that time, Peter wrote like 3-4 pages document just highlighting what we would need to do. But then in June, when I wrote a blueprint, which so now you probably know is a document which details all the steps that precisely that we will need to formalize in order to get to our goal. And that's also when we decided to follow particular parts of books or papers for different parts. And then once the blueprint was almost fully written, not quite fully, like the last parts were still a sketch, we announced the project, asked for contributions, and several people joined immediately, and we started formalizing everything, also refining the blueprint as we were going, because like when you formalize, you realize that things are not exactly how they're written in the LaTeX. I make mistakes when I write LaTeX, and also sometimes the way you write it is not exactly the best for the formalization. So it was adapted, but mostly it was first blueprint and then formalization. And now we, since the beginning, the goal of the project has been to add everything to MATLAB, because we are doing very well-known classical map that will be useful for probability generally. So we want everything in MATLAB, and that is still ongoing. So some remarks. So for the preparation phase, it was just Peter and me. So 2 people, and I write 3+ weeks because something was done 2 years ago. But for the blueprint writing, like the 30 pages of blueprint, that was like sometimes that was around 3 weeks, not full time, like 2 hours one day, 3 hours another. And but afterwards, when we called for collaboration and started formalizing, everything was just done in 3 weeks. there was there was no AI involved. It was just it was very capable humans formalizing lean, and I was very surprised by the short time that was needed to formalize. And then afterwards, I thought maybe I should not have spent so much time on the blueprint, and it would have been much more efficient to just involve more people directly. But that's how it went. So the blueprint is something that you've seen a few times, but I still want to show what it looks like. So that's our repository with some pull requests for the new developments that we are doing now. So the blueprint on the website is just some sequence of lemmas written in LaTeX. Here we see some check marks saying it has been formalized, but it's very much not written like a book. Like it's not just taking the proof from the book, cutting the proof in several small lemmas and putting it in a LaTeX, because you're not talking to the same people. Like somebody reading part of the blueprint has not read the previous chapter, maybe. Like most often, you should think of your blueprints more in the way represented on the dependency graph, in the sense that one contributor will want to formalize a node, and they will look locally around that node, and maybe they don't know what's really above, so they want to formalize. Yeah, that's not. Yeah, that the covariance thing that we claim that is a covariance matrix for our Brownian is actually a positive semi-definite matrix. Well, you want to write the blueprint in a way that they know exactly which thing they need to use, and they will look at that locally and try to implement it that way. So you don't say, like in a normal proof, you would assume that people know a bunch of properties of those Gaussians because they were explained a few pages before. Here you point exactly at, you use this lemma, use that theorem, and you try to guide much more. Also, another aspect is that constantly when writing the blueprints, you have to think about what is already in your code base or in MATLib. It's your book has a different idea of what is already known than MATLib. And so it's an exercise in going back, adding lemmas and definitions until you hit a definition that is already in MATLib, and then you can start going from there. So, yeah. So that green part here is the formalization of Brownian motion. So here on that side, there's Gaussian things. On that side, there's a continuity theorem, and we put them together to have the Brownian. And that big mess on the side is the current development for stochastic integrals, but I will come back to that. Yeah, so writing the blueprint has been and is for the new developments definitely the bottleneck of the project. At least in that part of math, there are many willing contributors who are ready to formalize a lot of stuff. And if you provide them with clearly defined tasks, they will formalize them super quickly, which is also a reason why I have not tried to play so much with AI. Is that my main job is to transform the LaTeX into formalized statements and post tasks telling people that it's ready to be formalized, and then 1 day later it's done. So yeah, that's for me really turning the informal math into something formalizable by people is really the bottleneck. Okay, so what we did formalize is a bunch of things about Gaussian measures. So we only really needed Gaussian measures in RD, but we took a detour because we want to add general things to MATLib. So we defined what it means to be Gaussian in a Banach space, prove things like the fact that in such a space, Gaussians have finite moments, and then specialize to Hilbert spaces and RD. MATLib had nothing about the relation between the finite dimensional distributions of stochastic processes and their their overall distribution. We defined a few things about modifications, what it means to be indistinguishable. The Kolmogorov extension theorem, of course, I already said that, and a big part of the work was the continuity theorem, for which we decided that it would be much more fun to not follow an old book, but a new paper. So we found that paper by Kretschmer and Rusov from 2023, and which uses a proof which is also interesting, like it uses Talleyrand's chaining technique to prove the theorem. And I was very much interested in that proof because I want chaining to do concentration inequalities later. So yeah, and putting everything together, we defined a Brownian motion, a real valued Brownian motion. Maybe at the putting it together step, we did not do something very general, but the tools before are general. So we have that Brownian motion, which is a stochastic process with some given finite dimensional distributions, which determine the whole distribution and has continuous path. So I want to focus, okay, on the blueprint, there were two equally big parts, everything about Gaussians and the continuity theorem. For this talk, I made the choice to focus on the Kolmogorov-Chentsov theorem. But I want to mention still that there is a lot of work on the other part. So we want a continuous modification. A modification of a process is another process such that at all time, it's almost surely equal to the original one. So in particular, they have the same distribution, but they are not necessarily indistinguishable. Indistinguishable would be that the almost sure equality holds for all time at the simultaneously. So that would be something stronger. Okay, and the Kolmogorov-Chentsov theorem is a sufficient condition to states some sufficient conditions on space and the process to be able to get a continuous modification. Actually, more than continuous, a earlier continuous modification, but in particular continuous. Okay, so what kind of assumptions and what kind of setting is is used by that theorem that we formalized? So we suppose that the time, so the index is some extended pseudo metric space. So metric space means there's distance. Extended means that the distance could be infinite, although for the time index it will not be. And that pseudo means that there could be two different points at distance 0. And we have a stochastic process xt with values in E. And we did some assumptions for that in order to be able to get a continuous modification. First one is on the time index set, which is that it has bounded covering number, so that's kind of a measure of dimension. So the covering number is the least amount of balls of some radius needed to cover the whole set. In particular, it means that T has bounded diameter, so its distance is not actually infinite. And the condition on T is that when the radius of the balls gets smaller and smaller, then the number of balls needed grows only in epsilon to the minus d. So in RD, for example, if you want to cover the unit ball, then you need order epsilon to the minus d balls. So that's some dimension assumption, and we need also kind of Hölder continuity on the expectation of the distance of the values of the process xt on that set. And if we have both of those, then big theorem says, yeah, there is a Hölder continuous modification. In particular, it's a continuous modification. So, yeah. Oh no, I had a remark about that. There is also a measurability assumption here in the Kolmogorov condition that I wrote. It's because we never assume that the space E is second countable. So having just xt measurable is not enough to have xs, xt, the pair measurable. In particular, it's not enough to have the distance measurable. So that's why we need to be careful with measurability of pairs a bit everywhere. In essence, the difficulty is that if E is not second countable, then the Borel sigma algebra on the product is not the same thing as the product of the Borel sigma algebras. Yeah, and that will be something I talk more about later. Okay, so we have that theorem which says that under those conditions, then there is, in the second part, if E is also complete and T is second countable, then there is modification with continuous Hölder path. Okay, that version of the theorem will not apply to R plus to give us the modification of the Brownian because it applies to something that has bounded diameter. So we will apply it to 0, 0n for any n, and then we will need to stitch together the modifications that we get from this to get a modification for the whole Brownian motion on R plus. I will not talk about the proof of the theorem. I will talk only about some things that we remarked while formalizing. First one is that in MATLib, there is much more things about measures than about processes or random variables because the measure theory part was developed first. And for example, to say that a random variable x has a law p in a space with a probability measure q, we could just write that the map of q by x is equal to p. That's the same statement, except that that map function in Lean is that map is only really well defined if x is almost everywhere measurable. So when you manipulate a statement that just is equality of map and you want to say that something about the law of a composition, for example, then you will have to give to Lean regularly proofs of almost everywhere measurability everywhere to say, yeah, that equality is actually making sense and it's not zero, and the map is not zero because of a default value. And so it was much more convenient to encapsulate measurability with the equality of map statement in a new predicate has law. So that's kind of considerations that you have when like that is not doing much, but it's easing the formalization of later steps because those you can just state composition results about that without having to input more proofs everywhere. Another remark is that when I wrote the blueprints, there were errors in the constant everywhere. The constant that we report at the end of formalization are also not those of the paper that we follow because of they've forgotten a very small edge case somewhere. And when we realized while formalizing a lemma that a constant was wrong in Lean, then you just change the constant and you get errors at the few other lemmas that actually use the value of that constant, and you know exactly where to change it, and it's a very easy process. When I wanted to reflect the change in the LaTeX blueprint, then I needed to go through in every line of the proof, check if the constant was already changed or not. And yeah, constants are much easier in Lean. Also something remarking, which is linked with the measurability of pairs that I talked about earlier, is that sometimes you realize while formalizing that you are not exactly using the theorem as stated in the paper, but actually you're using, like in that case, for the modification, you're using the shape of the particular modification that you build in the proof. The theorem is there exists a modification with that property. And I said that the theorem applies to a bounded set, and then we want to do it for several bounded sets to combine those modifications and have a modification over the whole of R plus. And when you do that and want to prove measurability of your modification in that case, at some point you will get from the theorem that says there exists, you get a first modification, then you get the second one, and at some point when you combine them, you need measurability of the pair of xs for the first modification, ys for the first, and yt for the second. And you realize that the theorem does not give you that. But then when you go back to the way you prove the theorem and the way you constructed the modification, then you see that actually that modification is built in a particular way. That means that you have that property of measurability of pairs for any two modifications that you would get from the actual proof of the theorem. So in our implementation, the theorem proves one more property of the thing, which is that it's actually written as a limit of the x's, like just over some indicators in the measurable space omega. And with that particular property that describes a bit the shape of the modification, then everything goes through. The way it was proved in the paper we followed was measurability follows from standard techniques. Yeah, I guess it does, but we were a bit surprised and had to refactor that and actually work on it to have the measurability. Another thing is that it's easy to track where assumptions are used, and it allows you to maybe first do a formalization where we, when we first finished the formalization of the continuity theorem, well, the space E was second countable, and so we had given up on that at some point, and at the end the space was second countable, so everything regarding measurability was easier. And the spaces were not pseudometric spaces, they were metric spaces, like points at distance 0 were equal, as in the paper we were following. But then it's super easy to just change the assumption that you declare somewhere in a variable line and see what breaks. So you see what breaks, well, when you get from metric to pseudometric, your equality is not meaningful anymore, so you have to replace all your equations with distance 0 statements. Okay, that's a bit of breakage everywhere, but it's not serious, you just do it. And then you see that there are two places where something much more interesting seems to be happening, and so you know immediately there are those two things to fix. And there was a discussion on Zulip, and I want to say that in particular, Sébastien Guezel gave many arguments and ways to circumvent the matrix space restrictions, and in the end we were able to generalize that assumption completely. So it's very local generalization. I'm not saying that, like, overall we followed every idea of the proof of the paper that we were using, like we did not change the proof in any significant way. It's just that in the end it's really easy to analyze the proof and do those marginal generalizations of your assumptions. Yes. Okay, one thing you might be tempted to do when you have a formalization project like that is say, okay, we want to formalize a Brownian, so the last thing in the project is definition Brownian motion. But that's not enough. Like, if you kind of want to check that actually what you call the Brownian motion has the properties you expect from a Brownian motion, like for you to be sure that it's the right thing. Also to check that your definition is actually usable in lemmas, that it's not too hard to work with, and that maybe you should define it in a slightly different way. So yeah, this is to say, in order to be sure, one way is to take a bunch of properties of that you know should be true for that object and prove them. So here's a list, like having stationary increments, some independence of the past that I mentioned, the law, the distribution of the Brownian, a bunch of transformations of Brownians are also Brownian, so we verified a few of them. Yeah, so that allows to check that we have the right definition, but maybe more importantly to check that we can actually upload that to MATLib because it seems usable. Even though maybe first we need a more general definition of Brownian that is not just a real valued one, maybe. Okay, so we did that whole Brownian motion formalization, and then at the end of that, what we have is a community of people who are formalizing probability together. And so we did not want to just stop the project. And then we picked another goal that is related. And that other goal is stochastic integrals. Now that we have a Brownian, we want to integrate a process against a Brownian. That's an ongoing project. In the blueprint that I showed, that's the huge blob of nodes, most of them white, meaning they're not done. The green was done, and here it says it was not. We are accepting contributions. There is a list of issues in the GitHub repository, and anybody can claim those issues. As I said, there is a blueprint bottleneck. So right now, every issue is claimed, and most of them are already done. And we are just waiting for people to actually produce tasks, like by checking the blueprint, making lemmas, and all of this. A big change in organization is that I'm not writing the blueprint alone. We are at least 4 who wrote different parts of it. And it's also concurrent with the formalization and all collaborative. So our goal is Ito's lemma for integrals against Cadillac-May martingales. So for those who know that, there is a list of things that we want to prove on the path, but I will not talk about it. We are making progress. I don't know, we might be done in 2-3 months, something like that. Yeah. Okay, so in summary, we formalized that. We formalized the Brownian motion, but maybe more importantly, we formalized some general tools, like we formalized Gaussians not just in RD, but more generally than that, so they can be used in other applications, as well as the Kolmogorov extension and Kolmogorov-Chentsov theorems. So we are making PRs to MATLib, and also on the project, we activate every linter, every code style thing that we can to fit to MATLib as much as possible. And we made like something like 60, I think, when I counted pull requests to MATLib. Most of the, maybe 2/3 of the Gaussian things that we developed are in MATLib now. The goal is for parts of the project to disappear from our repository as we go. And you can join the stochastic integral project. I will finish with announcements related to Lean conferences. So very soon in January, there is the Link Together online conference. So it's all virtual talks by Zoom over 1 week. And each day we change the time zone, like we change at which time we start and which time we end to try and accommodate people from all around the world. And also this summer at the International Congress on Mathematical Software, there will be several sessions that can interest people here, notably one on mathematics in Lean. There is another one on more like reasoning and AI and formal math. So the session list is there. Yeah, that first one, automating mathematical reasoning. And well, there are many other sessions that could interest you depending on what you do. And with that, thank you for your attention.
Thank you, Rémy. So I think we have time for a couple questions, actually. So is there any question from the public?
Thank you, Rémy. I'm curious to understand, as a project manager, there are several constructions of Brownian motion that are possible. You choose the Kolmogorov extension route, but you could have used, the Levy constructions, or the more general, Gaussian measure on Banach space, but then you need the Cameron-Martin theorem.
Yeah.
Can you comment on what is the thought process on which strategy to pick before starting the project?
Well, in that case, the formalization of the extension theorem came first without thought about the overall Brownian motion strategy. So then we said, okay, we have that one. Let's go from there. So that's obviously an important part. You look at what's already there, formalized in MATLib or other repositories, and then take the path of least resistance. I mean, it depends a lot on your goals. If you just want to go there quickly, maybe do that. If we just wanted to go there quickly, we would not have done the Gaussians in Banach space. If you want to contribute to MATLib, then one important factor is that along the way, you prove interesting things that can be reused later. But okay, if you have maybe chosen an overall strategy, then in that strategy at each step, you will want to find maybe some proof that is more amenable to formalization, in the sense that you will prefer some more conceptual proof and avoid anything that is more computational. Yeah, there are. Then, yeah, that's.
Thanks.
Any other question? So I would like to ask one thing, actually. You mentioned generalization. So it happened in the project that you realize, oh, I don't need this hypothesis, or I just need a weaker version of it. And do you foresee that as being like amenable to automation, either by just simple, I don't know, continuous integration tools that point out very obvious things, or even by more complex and maybe AI-related tools?
Well, the first tool that could be used is something that just tries to replace one assumption with another, and if nothing breaks, it reports that. There are issues where sometimes you get to something that's not mathematically interesting anymore, but okay, yesterday we were coding and we observed that for one lemma in the project, a linear order was assumed while a partial order was enough, and yeah, that was an easy change. It could be very automatic. But most often, when you have an assumption available, you use it in the proof because it's easier. Like, for example, when we finished the proof with the second contability, with the metric space assumption and not pseudometric, well, it's much easier to just chain equalities than to state distance zero properties everywhere. So the code was full of equalities. I guess it's not hard to refactor for an AI, that kind of thing, because it's very systematic. You just do the same kind of change everywhere. So yeah, that could be a good tool.
So thank you.